All right, example 8 starts talking about interest, and so we'll use an exponential formula for interest. Here is our formula. If we have n compoundings per year, so if we compound our interest monthly or daily or even by the minute, but continuous compounding is what happens if every possible instance we are compounding our interest. So if it's continuous compounding, we're going to use the second formula, P natural base e to the RT. All right, so let's go take a look at these three problems actually. We're going to take $12,000 invested annually at 9%, and we're going to find our balance after 5 years if it's compounded quarterly, then monthly, then continuously. So for A and B, we're going to use our first formula. We're going to find out our A. And so let's do our first one. The principal, P, is 12,000. 1 plus, what's our rate? 0.09. We want to put in 9% as a decimal. And then n is how often we're compounding. Quarterly, we're going to compound 4 times a year. And so again, n is 4, and t is how many years we're doing this for. We're doing this for 5 years. Okay, so if we plug all of these things in, we're going to end up with a final answer of $18,726.11. If you plug that in properly with the proper order of operations. Let's take a look at the second one here. The principal stays the same. The 0.09 stays the same. We're still getting 9% interest. But this time we're going monthly, which means that not 4 times a year, but 12 times a year we get our interest, and so then 12 times 5 for our exponent. Doesn't change our answer that much. We change to $18,788 and 17 cents. So we are getting an extra $60 a year, but not a crazy increase. And then lastly, we can use our continuous compounding formula. A equals 12,000, and then E to the 0.09 times 5. Do the order of operations correctly, and you'll get $18,819.75. So again, an increase, but not a crazy increase. All right, so see if you can do a compounding problem on your own. 59 is our problem. Pause this, press play when you're ready. All right, our formula is going to look like this. A equals 1,500. 1 plus 0.02 over. And then on this one, our n is changing actually. So what I'm going to do here is I'm going to put in, just leave it as the variable, and leave this as 10n up here, because we know t is 10. So we can actually simplify this and put it in our graphing calculator and let the table do all of the work for us. So let's go ahead and see how that's going to look. So let's go to our y equals, and move this over so we can see it. Let me clear it off. 1,500 times 1 plus 0.02 over x, and notice I don't need parentheses here because order of operations is going to divide first and then add. So I'll close my parentheses and then raise it to the 10x. And let's go ahead and use our table set to start with 1. And then we'll count by ones. And let's go ahead and see what our table tells us. So in year 1, we're going to make $1,828.50. That doesn't seem right at all. Let me check our y equals, see if I made a mistake here. Alright, so I found my mistake here, and the problem here is that I wasn't putting the 10x in parentheses. So without the parentheses there, it's taking the whole thing, raising it to the 10th power, and then timesing by x. So we got to put our entire exponent in parentheses. Go back to our table here, and so we have $1,828.50 for 1. For 2, $1,830.30. 4, $1,831. If we want to get to 12, we would have to go down here. At 12 years, $1,831.80. 365. I don't want to scroll down that far, so I'm going to hit table set and start at 365 and let it figure it out for me. Go back into my table. If we do it 365 times a year, I'll make $1,832.10. And then if we want to go continuously, then we'll have to use a different formula. So we'll use this A equals 1,500 e to the RT, so 0.02 times 10, which is 1,500 e to the 0.2. And if you do that one correctly, you should have ended up with $1,832.10. So that's the most you're ever going to make, is if you compound continuously.